In this video I'm going to go through a lead answer question. Came up in 2015 on fuels and thermochemistry. So this one begins with fractional distillation. It says to identify a property of a hydrocarbon that results in its presence in a particular fraction. So we know crude oil is a viscous mixture of hydrocarbon molecules. We heat up the hydrocarbon molecules, and as we heat it up, the molecules separate based on their boiling point. As they're all hydrocarbon molecules, the boiling point will just depend on the intermolecular forces, which are van der Waals forces of attraction between the molecules. So essentially what we have is the longer chain molecules, or the bigger the molecule, the more points of contact between like molecules, and so the greater the van der Waals forces of attraction between those molecules. And therefore, the longer the molecule, the higher the boiling point. And conversely, the shorter the molecule, the lower the boiling point. So if you heat something up and you put it into a very tall column, the shorter molecules will, as the column gets further and further away from the furnace where you've heated it up, the temperature gets cooler. And so as the molecules themselves are shorter, they can remain a gas at a lower temperature because their boiling point is lower. So therefore, we can separate out the molecules based on their boiling point. So it says identify a property of a hydrocarbon that results in its presence in a particular fraction. That is going to be the boiling point of the molecule. You could say size of molecule, etc., but effectively it's just the boiling point. Name the fraction obtained from crude oil that's used as fuel for jet aircraft. This is a bit of recall from crude oil. To get more on this, you can have a look at the website, which I'll just put up now. So we can see there are fractions from crude oil, that the fraction that's used in aircrafts, like for fuel for aircrafts, is kerosene. So you're just going to have to learn off those fractions and their uses, as any of them can come up in the leaving cert. But as you go higher up the column, the molecules get smaller because their boiling point is essentially lower. So they can remain a gas at a lower temperature, which is further from the furnace. So now just going back to the question, we know that was kerosene. What process is used to convert molecules in this fraction to smaller molecules that are in greater demand? That process is called cracking or catalytic cracking. We've answered that a few times. It's where a catalyst and heat are used to take a longer chain molecule and break them up into smaller molecules, which obviously are in more demand, but usually we can create an alkene and an alkane from that, and from the alkene we can make various products that could be quite useful, like polymers and things like that. So C, what are the two reference hydrocarbons used to assign octane numbers in fuel? So an octane number is a measure of the tendency of a fuel to resist this process called knocking or auto-ignition, where the fuel ignites too early. And you get pre-ignition of the fuel, which results in a knocking in the engine. So the worst molecule for that is something called heptane. That's given a result of 0. And a molecule which is given a result of 100 is something called 2,2,4-trimethyl pentane. Give two advantages of adding oxygenates, such as ethanol, to petrol. The two main effects there for adding any kind of oxygen to a molecule, which is called an oxygenate. The standard one is MTBE, methyl tert butyl ether. When we add these to the fuel, the octane number will be reduced. So it reduces the auto-ignition. Lead used to be used, but it's toxic. And another advantage, if you're adding more oxygen, then it allows for more efficient combustion. So you get cleaner combustion, and so less pollution. So we reduce auto-ignition, and we reduce pollution because we burn the fuel more efficiently. So now we're on to the calculation part. So I'm going to do this in a bit of space down here. It says to calculate the heat of formation of ethanol, given that the heat of combustion of ethanol is this. There's a number of ways to do this. I'm going to start by writing out the equation that we want. It says calculate the heat of formation of ethanol. So essentially the heat of formation of ethanol is the formation of ethanol, which is C2H5OH, and we form it from its elements. So there's 2 carbons, there's 6 hydrogens, so that's 3H2 in their standard states, plus half O2. So that is the enthalpy, or heat of formation, of ethanol, because it's a formation of 1 mole of a substance from its elements in their standard state. Now it says, given that the heat of combustion of ethanol is this, and the heat of formation of carbon dioxide and water are this. So what I'm going to do down here is use a Hess cycle to answer this question. So it says, given that the heat of combustion of ethanol is this. So when I take ethanol and I burn it, the products I produce are carbon dioxide plus water. So that's when I burn anything. So here we can just balance it by getting 2 of those and 3 of those. So I'd obviously have to add an oxygen to burn that, but we don't need to write that into the balanced equation. Now, it's telling me that the heat of combustion of ethanol, so from going from ethanol to my gaseous products, that heat of combustion, which is burning 1 mole of a substance in excess oxygen, is minus 1370.7 kilojoules per mole. It says that the heat of formation of carbon dioxide and water are this. It could have told me that the heat of combustion of carbon was that, or the heat of combustion of hydrogen was this, but it specifically wanted to just test your knowledge here. It says the heat of formation of carbon dioxide. Well, the heat of formation of carbon dioxide is forming 1 mole of carbon dioxide from its element. So if I'm forming carbon dioxide, then the heat of formation of carbon dioxide is minus 393.5. But here I'm forming 2 of them, so for that arrow I'm going to need to multiply it by 2. It says the heat of formation of water is minus 285.8. But you can see that I'm forming 3 moles of water, so that's multiplied by 3. To answer this question, we are going to be using a Hess cycle. So ideally, I want to find that energy change. Hess's law states that the total energy change is independent of the route taken. So while I want this highlighted yellow version of an energy change, as long as I'm going from those reactants to that product, the overall energy change of the yellow arrow and the green arrow are the same. So delta HF is equal to, well, these green arrows here and there are going in the right direction, as in they're going from reactants through to products. So it's going to be minus 393.5 times 2 plus minus 285.8 by 3. Now, the energy change for the ethanol reaction is going in the wrong direction, because that energy change is going this direction. Okay, it's going in the reverse of my highlighted green arrow. So really I want the information that's going in that direction. So that energy change of this orange arrow is going to be the reverse of that figure. So instead of adding it to the green figures, all I do is I subtract it. So it's going to be minus 1370.7. Likewise, I could have said that this is delta H1, this is delta H2, and this is delta H3, which is the energy changes, and that delta HF is equal to delta H1 plus delta H2 minus delta H3, because it's going in the wrong direction. So that's the energy change of the reactants minus the products. So essentially what I'll do, and in the leaving cert it's probably worth your while, going through to this step here and writing out what each of these figures are. So the carbon one becomes minus 787.0. The hydrogen one becomes minus, and we're just adding a negative number, so it's just minus 857.4. And this is minus minus, so it's a plus 1370.7. So when we add up those figures in the calculator, I get a figure of minus 273.7 kilojoules per mole there. So this is why I always advocate for drawing a Hess cycle in the reactions, because if you have an understanding of the energy changes, it's worthwhile doing. The last part of that question there, give two properties of hydrogen that made it fuel of choice for the space shuttle. Well, hydrogen is not very dense, so it's very low in density. Also, hydrogen has got a very high energy content. It's really easy to burn. So what you'll notice before in the Lebenser text is that they talk about the high calorific value. Okay, so it's got a very high heat of combustion. It's non-polluting, any of those kind of things. It is also very dangerous because it's so flammable. But hydrogen, we can say it's non-polluting, it's got a low density, high energy content, any of those. So state one difficulty then, it's explosive. Because it's a gas, really flammable, it's very dangerous. Like, as it's a gas, it can leak easily and things like that as well. So give two ways in which hydrogen gas is produced in industry. Well, to produce it in industry, in one of the fuels topic, we talk about taking a molecule and increase this octane number. Now, to increase this octane number, you can carry out a process known as dehydrocyclization or reforming. That's one way of making hydrogen as well. Okay, you could take it from the electrolysis of water. Also, steam reforming of natural gas. So when you have natural gas, what you can do is you can, which is methane essentially, you can react it with steam, which is water vapor, and a catalyst, and you produce carbon monoxide and hydrogen. And that's one way of getting hydrogen. Sometimes the hydrogen is used for a fuel, or sometimes it's used in the production of ammonia when reacted with nitrogen. So that is that video there on fuels and thermochemistry from 2015.